Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 25. Phi Communication Systems. Speaking across distance. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We begin a new book, Information Systems. We have learned to engineer physical structures. Now we turn to engineering meaning. How do we use phi to talk, to remember, to think, and to connect? We enter the communications hub. Rows of sleek, silent transceivers line the walls, not blinking with simple LEDs, but displaying live holograms of their transmitted phi fields, swirling vortices of light, intricate phase patterns on radio waves, pulsing sonic landscapes. This is not just sending ones and zeros, this is sending shapes of change. Your new skill is that of the communication architect. You are learning to design systems that encode information not in the amount of something, but in the pattern of its phase across time and space, leveraging the coherence of phi to speak across distance with unprecedented resilience and capacity. Scene: the communications hub. The air is still, but alive with intention. At one station, a technician watches a screen showing a laser beam traversing a chamber of swirling, heated air, simulating atmospheric turbulence. The beam doesn't just dim or flicker. Its wavefront, visualized as a color-coded phase map, wrinkles and folds. Yet, the data stream beneath it remains a solid green bar. 10 gigabits per second, zero errors. At another station, a display shows an underwater acoustic channel. Instead of a simple ping, the visualization shows a propagating torus knot of sound pressure, a topological message twisting through the murky water, immune to the echoes that scatter simpler pulses. Your console presents the core challenge. On one side, a channel model. Turbulent free space optical, coherence length 2 centimeters, bandwidth 10 gigahertz. On the other, a library of Fa modulation schemes. QPSK, classical, orbital angular momentum, OAM, multiplexing, topological charge shift keying. Your task is to choose or design the scheme that will conquer this specific channel. Our puzzle is one of matching grammar to environment. Given a physical communication channel with its own noise and distortion characteristics, its own accent, how do we design a phi encoding scheme that is maximally resilient to those distortions, and how do we prove it outperforms the best classical methods? We are moving from speaking the language to designing the telephone line. The language role, the channel-specific encoding skill. This POW teaches a systems design skill. It is the skill of exploiting the structure of a physical channel's noise and dispersion by encoding information in phi dimensions that are naturally robust to that channel's specific distortions. Our core question about phi is, given a communication channel defined by its transfer function, how it transforms an input phi field into an output phi field, what is the optimal set of phi patterns to use as symbols, patterns that remain maximally distinguishable after passage through the channel? And how do we synchronize transmitter and receiver to a shared phase reference to decode them? We are moving from making beautiful sentences to ensuring they are heard clearly through a storm. The anchor image, the conductor, and the noisy hall. We will use the anchor image of an orchestra conductor performing in a cavernous, echoey cathedral. The classical communicator is like a solo trumpeter playing loud notes, amplitude modulation. The echoes blur the notes together. The phi communicator is the conductor with a full orchestra. They don't just play louder, they use complex, tailored sound shapes. They might use a sustained chord from the woodwinds, whose phase relationships are preserved even as the sound reflects, or a rhythmic pattern from the percussion that echoes creates a predictable, decodable pattern. The conductor, the encoder, and the listener in the best seat, the decoder, share a common score, phase reference. They are using the structure of sound itself to defeat the structure of the noise. The coherent selection principle in communication. In communication, coherence is the carrier of distinguishability. Constructive resonance, alignment, in communication means the received phi patterns, symbols, are coherent and distinct. They add up cleanly at the receiver, allowing clear decision boundaries. This was symbol A, not symbol B. Destructive resonance, dissonance, means channel noise scrambles the phase relationships. Symbols blur into each other. Phase lock is lost. The message becomes incoherent noise. The communication architect's mantra is about preserving integrity. If coherence breaks, we stop. If coherence returns, we continue. If the receiver loses phase lock with the transmitter, it stops trying to decode and sends a signal for resynchronization. It does not guess, creating cascading errors. Core mechanisms: phi modulation, coding, and benchmarking. We have a toolkit for coherent communication. 1. Phi modulation schemes, the alphabet of shapes. We move beyond simple amplitude or frequency. We encode bits in features of the phi field. Phase shift keying, the classical bridge. We shift the phase of a carrier wave by set amounts, 0 degrees, 90 degrees, 180 degrees, 270 degrees, to represent bit pairs. This is a 1D phi encoding along the time-phase axis. It's vulnerable to phase noise. Spatial phi modulation, OAM multiplexing. We use different orbital angular momentum modes of light or sound as parallel channels. A beam with a helical wavefront, charge plus 1, is symbol A, charge plus 2 is symbol B, etc. These modes are orthogonal. They can, in principle, be separated even if they overlap. This exploits the space echo. Topological encoding. We encode in the topological charge of a defect. A vortex of charge plus 1 is a 1, charge minus 1 is a 0. Topology is robust. Bending or weak scattering doesn't change the integer charge. You measure it by the total phase around the loop. This is a digitally robust phi encoding. Waveform shaping, multidimensional. We don't use a single carrier. We design entire complex phi patterns in spacetime as symbols, optimized to be far apart in the space of possible patterns after the channel distorts them. This is like the conductor's custom chords. 2. Channel coding and error correction in phi space. We don't just send raw symbols. We add redundancy in a phi-smart way. Phi lattice codes. We map our symbols to points on a lattice in a high-dimensional phi space. For example, the space of possible phases across an array of antennas. We choose lattice points that are far apart even after the channel's typical distortions. This is error correction by design. Differential encoding. If absolute phase reference is hard to maintain, for example, in a fast-fading radio channel, we encode information in the difference in phase between two successive symbols or two adjacent spatial channels. The channel may rotate both, but their difference may be preserved. Synchronization, the shared heartbeat. This is the linchpin. Transmitter and receiver must share a phase reference. How? Pilot tones. We dedicate a small fraction of the bandwidth to transmitting a known, stable phase reference. Clock recovery circuits. The receiver uses nonlinear processing on the incoming signal to extract and lock onto the timing, omega, and phase rhythm. Differential schemes. As mentioned, they avoid the need for an absolute reference by being self-referential. 4. Ruthless benchmarking. This is our discipline. Any claim of a phi advantage must be proven against the best-in-class classical system under fair conditions. Same total transmitted power, same bandwidth, same latency, same channel model. Bit error rate versus signal-to-noise ratio, the gold standard curve. We plot how often bits are received in error as we reduce power, lower SNR. A better system has a steeper curve, fewer errors at the same SNR. The coherence criterion, shared reference and channel support. Our coherence criterion for a viable phi communication link is two-part. 1. Shared phase reference or robust differential scheme. Transmitter and receiver must be synchronized in phase or use an encoding that doesn't require it. 2. Channel coherence support. The channel must preserve phase relationships over the symbol duration and across the spatial aperture. The coherence time and coherence length of the channel must be longer than the time-length scale of our phi symbols. You cannot send a complex spatial pattern through a channel that scrambles it faster than you can detect it. If either criterion fails, phi modulation fails. You fall back to incoherent, energy-based detection, losing the potential advantage. The dissonance indicator, loss of lock and intersymbol interference. The primary dissonance indicators are loss of phase lock and intersymbol interference, ISI. Loss of phase lock. The receiver's internal oscillator can no longer track the incoming phase. The received constellation diagram, a plot of received phases, becomes a spinning, blurry circle. Decoding becomes impossible. This is often caused by phase noise or Doppler shift exceeding the tracking bandwidth. Intersymbol interference, ISI. The channel is dispersive. Different frequency components travel at different speeds. This smears one symbol's phi pattern into the time slot of the next, causing them to interfere. In spatial multiplexing, like OAM, this appears as crosstalk between modes. The +1 vortex gets smeared, leaking energy into the +2 detector. Seeing these indicators means your chosen phi modulation scheme is mismatched to the channel. The coherence of the message is destroyed. The safety rail, fair benchmarking and physical limits. Our safety rail is intellectual honesty and physical law. 1. Fair benchmarking mandate. Claims of superiority for a phi system are invalid unless demonstrated in a blind, independent test against the best classical alternative, with all parameters, power, bandwidth, coding overhead, equalized. No hidden advantages, like using more bandwidth secretly. This rail prevents hype and ensures progress is real. 2. Physical limit acknowledgement. Phi systems are bound by the same ultimate limits as classical systems: the Shannon limit on channel capacity, the diffraction limit on spatial resolution, and the coherence limits of the channel itself. A phi system cannot magically send infinite data with zero power. Any claim that appears to do so is false. The safety rail rule. No phi communication design is approved for deployment or serious consideration without a fair benchmark analysis proving a specific, measurable advantage under defined conditions. A measurement scene. The turbulent laser link. Let's enact a roadmap's measurement scene. Scene. Sending a file via laser link through laboratory-generated turbulence using hot air, comparing fine-coded orbital angular momentum, OAM modes, versus classical amplitude shift keying, ASK. Turbulent air. Coherence length 1 centimeter, coherence time 1 millisecond. Strong scintillation, intensity flicker, and phase distortion. Classical system, ASK, modulates the laser's intensity. Receiver measures power. Vulnerability. Scintillation causes deep fades, moments of near zero intensity causing burst errors. FA system, OAM, uses a spatial light modulator to create beams with helical wavefronts, OAM modes +1, +2, +3. Receiver uses a mode sorter, like a hologram, to separate them onto different photodiodes. Promise. The phase structure of the vortex might be preserved even if the intensity pattern is distorted. The pass, phi advantage realized. Divisive. 1. Fair setup. Both systems use the same laser average power, same bandwidth, symbol rate, same error-correcting code overhead. 2. Measurement. Transmit a long pseudo-random bit sequence. Measure BER as laser power is attenuated, decreasing SNR. 3. Result. The BR versus SNR curve for the OEM system lies below the ASK curve. At a target BR of 1 engine minus 6, the OEM system requires 3 dB less power, half the power. The received OEM spectrum shows clean peaks at the expected modes with low crosstalk. Pass. The phi system's use of spatial phase structure provided inherent resistance to intensity scintillation. The fail, no advantage or worse. 1. The turbulence is so strong it completely scrambles the phase front faster than the receiver can adapt. The vortex beams are unrecognizable, mixing completely. 2. The BR for OEM is higher than for ASK at all SNRs. The advantage was theoretical and collapsed under real, strong turbulence. 3. Fail. The phi scheme is not suitable for this channel. The safety rail of benchmarking prevented a costly, failed deployment. The prediction spine. The hallmarks of a true phi advantage. A well-designed communication system yields a specific prediction spine. 1. Noise-specific superiority. A phi system designed for a specific noise type, for example phase noise, will show a steeper BER versus SNR curve in that noise than a classical system optimized for a different noise type, for example amplitude noise. The advantage is contextual, not universal. 2. Topological error cliff. For topologically encoded messages, for example using defect charge, the BER curve will show an error cliff, near perfect fidelity, BER 0, until the noise crosses a threshold that causes topological charge to flip, for example a vortex pair nucleates, then the BER jumps dramatically. This is a signature of digital robustness. 3. Multipath resilience. In a multipath fading environment, like radio in a city, a phi system using coherent combining or wavefront shaping from 10.4.2 will achieve a higher channel capacity than a non-coherent system because it can use the multiple paths constructively rather than suffering from destructive interference. Falsifiability, when the new phone is just a worse radio. Our falsifiability threads are brutal market tests for ideas. Falsifier 1, the phantom advantage. If, in rigorous blinded fair tests, a phi system shows no measurable advantage over the best-in-class classical system for its intended purpose and channel, then its claimed advantage is theoretical, not practical. It might work in a simplified simulation, but fails in the real world with all its complexities. The idea is falsified as a practical engineering solution. If a proposed phi system requires impossible coherence lengths or times to function, for example, maintaining phase lock across interplanetary distances with moving terminals through the solar wind, then it is not viable for that scale. The idea is falsified for that application. It might work in a lab, but not across the solar system. These falsifiers ensure we pursue only phi advantages that are real and deployable, not just mathematically elegant. Triunity in communication. A phi communication system is triune in its very essence. Time echo, symbol rhythm. The temporal sequencing of symbols, the clock, the carrier frequency omega. This is the heartbeat of the link. Space echo, spatial pattern. The shape of the wavefront across the transmitter array or aperture, OAM, beamforming. This is the face of the message. The journey of the phi pattern through the channel, its distortion, its fading, its delay. This is the narrative of the message's travel. Designing a good system means understanding how the channel's triunity, its temporal spread, spatial blur, and dynamic distortions, will affect our chosen time and space echoes, and choosing a modulation whose motion echo, the received pattern, remains decodable. Lanterns across scales, the grammar of connection. The principles of phi communication apply wherever information moves. Near scale, chip-to-chip optical interconnects. Inside a computer, using different OAM modes of light on a single waveguide to create multiple parallel data lanes, dramatically increasing on-chip bandwidth without more wires. Using topological solitons or specific phase-coded pulses for sonar communication between submarines. The phase structure can be designed to be less detectable by passive listeners and more resilient to ocean reverberation than simple pings. Far scale, future upgrades might use phase-stabilized optical links from distant probes. The extreme challenge is maintaining phase coherence over astronomical distances and years of travel. This falsifier number 2 looms large here, defining the ultimate limit of coherent interstellar communication. The ethics of the channel, fair access and truthful claims. The ethics of phi communication is about truth in engineering and equity in access. 1. Truthful benchmarking. As our safety rail demands, we must be brutally honest in performance claims. Overhyping a phi system as a revolution when it offers a 5% gain in a niche scenario is a lie that wastes resources and breeds cynicism. Ethics demands transparency in limitations. 2. Access and spectrum. If a phi system, like OAM multiplexing, can indeed pack more data into the same frequency band, who gets to use it? Does it exacerbate the digital divide or create new monopolies? The phi economy must answer this. The engineer must design with interoperability and open standards in mind to prevent lock-in. 3. Covert channels and eavesdropping. The resilience of topological modes could be used for secure military comms, but also for covert criminal networks. The ethical duty is to publish the principles openly, security through openness, while designing systems where the physical layer properties, like the need for a shared phase reference, provide natural barriers to casual eavesdropping, without relying on security through obscurity. The power to shape information in the fee domain brings the duty to be honest about its capabilities and to consider who benefits from its shape. The recognition skill, seeing the fee opportunity and noise. You know you need this skill when you look at a communication channel's failure mode and see a structural opportunity. When you see radio signals fading due to multipath interference, you think, what if we could control the phase to make the paths add up correctly? When you see optical signals scattered by fog, you think, what if we encode it in a property that scattering doesn't randomize, like topological charge? When you see crosstalk in a multi-conductor cable, you think, what if we use the coupled modes themselves as orthogonal channels? The moment you stop seeing noise as a random enemy and start seeing it as a structured distortion that prefers certain phi dimensions over others, you are thinking like a phi communication architect. The solution is to encode in the dimensions the noise ignores. The master tree location. This part, 10.5.1, is the foundational node of book 10.5. It depends on 10.1.3 for the basic idea of encoding, on 10.2.1, 10.2.2 to measure the channel and the received phi field, and on 10.4.2 to generate the complex transmitted patterns. It is the first application of information theory to the phi paradigm. It enables the construction of larger networks that use these links and influences the economic systems that will value and trade this new form of bandwidth. This is where information becomes a fluid shaped by phi grammar. Return to the phi. Let us zoom out. Communication is the coordinated shaping of a phi field in one place to induce a predictable, decodable shaping in a phi field somewhere else. The channel is the natural phi dynamics that connect the two places. Noise is the incoherent part of that dynamics. Our modulation schemes are carefully chosen clauses in the phi language that are grammatically robust to the channel's dialect of distortion. We are not just sending energy, we are sending structured coherence, a tiny intentional echo of the universal field designed to survive its journey and be recognized at its destination. Zenodo and the equations of the line. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. The papers detail the information theoretic capacity of OEM channels in turbulence, the design of lattice codes for phase synchronous detection, the statistical models for topological charge error rates, and the rigorous benchmarking methodologies that separate real advantage from simulation artifacts. They provide the rigorous foundation that turns the beautiful metaphor of phi communication into a quantitative engineering discipline. Closing. So, picture yourself in the communications hub. The benchmark test is complete. The graph on your screen is clear. The green curve, OAM, lies decisively below the red curve, ASK, across the operational SNR range. The annotation reads, measured advantage, 3.2 dB at BER 1E-6. Conclusion, phi system validated for moderate turbulence. You have just designed and validated a new way to speak across a storm. You have used the grammar of phi to find a whisper that outshouts a shout. This is part 10.5.1. Phi communication systems, speaking across distance. It is the opening of book 10.5, the moment we learn to turn physics into conversation. In our next session, we will take the information we can now send and learn to store it. We move to phi storage and memory. We will learn to write phi patterns into persistent media, not just as frozen sentences in materials, but as rewritable, addressable memories that hold the shape of change itself. We will learn to build the libraries of a phi-literate world. Remember, one field, phi, with its infinite echoes. We have learned to send its echoes across space. Now, we will learn to make them pause and wait for us. Salam and peace be upon you.